We are going to continue our journey here with optimization problems, applied minimum and maximum situations. So here's our next problem. A farmer has 3,200 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the rectangle that will produce the largest area? Okay, so notice that the question is asking what are the dimensions of the rectangle, and we're looking for the largest area, so we're going to need an area function to find the derivative of. So let's take a look at the picture. We have a rectangular situation with a river on one side, and we don't need any fence. So these two sides are the same, and then this long side here. So remember, the objective function is the function we need to find the maximum or minimum of. In this case, it's going to be area. So the area of this rectangle would be x times y. But there's two variables in there. So let's go to the constraint. The constraint in this case was the amount of fencing. That's a perimeter situation. So the perimeter is x plus y plus x, or 2x's plus 1y equals 3,200. We need to use this equation to make it so this is in one variable. So it doesn't really matter which variable you solve for here. Y is the easiest one to get by itself. So I'm going to subtract the 2x and get y there. And now we can plug that in. So instead of it being x times y into our objective function, it's actually x times this equation for y, or this expression. And now, because we're going to take the derivative of this eventually, I'm going to distribute and write it like this so we can just easily use the power rule when we're ready. But let's talk domain first. So talking about x here, the values for x, the smallest it could be is 0, because it can't be negative. And if it was 0, then that means we just have like a line here, basically, one big long fence, and y would be 3,200. If y was 0, though, like that, so x equals 0 is our low end. Our large end would be if this was 0, and basically we have two pieces of fencing that are like right next to each other. Like these would be right in the middle here. So think about it. If we have 32 feet of fencing and this is 0, then x would have to be half of 3,200. So the largest value for x is going to be 1,600 in this case. Okay, so derivative, just 3,200 minus 4x. Set that equal to 0. Find the critical points. So add the 4x to the other side, divide by 4, and we get x equals 800. Perfect. It's like right in the middle of our domain. Not that that matters, but it's within the domain is what matters the most. So now let's test it. At this point, I personally like the second derivative test. That's why I have the second derivative there. But honestly, you can go to the first derivative test and go here. You found your critical point, which is 800. And then you can say, like, a prime of whatever number you want here. It doesn't really matter. I don't know. I'll pick 5. I could pick 799. Doesn't really matter. As long as it's in the domain. Either way, you just pick a number less than 800, a number greater than 800, and then you determine if you have positive or negative. Well, this one's obviously going to be positive because it's like 3,200 minus 20. And then this one, 4 times 801, well, 4 times 800 is 3,200. That would give you 0. So if it's bigger than 800, then it's going to give you negative. So this is the first derivative test here, where you make the sign chart and you plug numbers into the first derivative. And then now, because you have a positive and a negative, the sign of the derivative changed, meaning the tangent lines are going to look like this on our position function. And 800 is where it's flat. So that proves that there's a maximum. But I like the second derivative so much better because it's just faster in my world, I think, in my head. So if this is the first derivative here, second derivative is -4. And Normally, there's an x to plug in and then you determine concavity, but if it's a constant, it means that it's forever negative. It's forever concave down. The second derivative is forever negative. I should say that the wording is off here a little bit. The position function is forever concave down because the second derivative is always negative. It's constant. So that shows that there's a maximum because concave down looks like this. And it's happening at the critical point. It's actually happening everywhere. Okay, so that we just have to prove that there's a maximum. Moving on, let's go back to the question now. So it asks for the dimensions. Well, x is going to be 800. So each one of these is going to be 800. And now we just need to use the perimeter equation and figure out what y is going to be. And in this case, it'll be 1600. So that's our final answer. Okay, let's do another one. If 96 centimeters squared of material is available to make a box with a square base and a closed top, find the maximum volume of the box. So we're finding maximum volume of a box. So we need to find a volume equation. That's what we're eventually going to take the derivative of. So here's our situation. The volume of this box, it has a square base. So x and x are the same here. And then the height we don't know, so it has to be a different variable. So our objective function is going to be the volume of this, which would be x times y. And the constraints in this problem represent the 96 square centimeters of material to make the box. So that's surface area. So think of surface area. We've got the bottom, which is x times x, and the top, which is also x times x. We're talking about area. So we have 2x squareds, and then these pieces, the faces are x times y, and there's 4 of those to go around. So we have x squared and x squared representing the top and the bottom, and then 4 xy's that represents the sides. And we have 96 square centimeters of material to make this. So there's our constraint. I see a typo here. Let me put this in here. That should be in there. I'm sorry. Oh, hey, I'm sorry. My bad. This is actually just a y. Sorry about that. I forgot the y. Okay. So now we need to use this constraint to rewrite this in one variable. So notice that there's 2 x's in this problem, so it's going to be hard to get x by itself. We can't really do that. So let's solve for y in this case, the y that wasn't there. Should have been. So the best thing here is to subtract the 2x squared to the other side, and then we're going to divide by 4x. And now we can plug that into the volume equation. It's kind of messy. We can simplify it though a little bit. And just, it doesn't really matter how you do this. I distributed. We could have canceled an x first, but I just brought the x squared and the 96 together and the x squared and the 2x squared together. But now you really can divide everything by 4x. And 96 divided by 4 is 24. X squared over x gives you 1x. And then 2/4 is 1/2. X to the 4th over x gives you x cubed. So I'm doing this. I mean, I could have kept it like this and then taken the derivative of this using the quotient rule. But it's just easier if you can divide both terms by the denominator. And now we can use the power rule. It's a lot better. A lot easier, I guess we could say. Okay, let's talk domain. Okay, so again, we can't have any negatives for x. Remember, domain talks about the x. So x, the smallest it can be is 0, because if it's 0, we just have a straight line of height, and that's it. So that's the smallest x can be. The largest it would be if this was 0. If this is nothing, then we have like flat piece of paper, I guess. It's like two-dimensional. So if y is 0, let's go back to this equation here. If y is 0, then we're left with this because this term will go away. And we'd end up with this. So this is the largest that x can be. It's going to be the square root of 48, largest x can be, which is approximately 6.9. So there's your domain. You just kind of look at the picture and go, okay, x obviously can't be negative. The smallest it can be is 0, which means that you don't really have a box. We have like a one-dimensional situation. But it's, that's not going to happen usually. And then the largest it could be is if this one was 0. And then you just plug in a 0 for the y, solve for x, and that tells you the large one, or the high point on the domain. Okay, because we need to use those on our sign chart. Okay, so let's take the derivative. 24, and then the power rule for this one gives you 3/2, and then subtract 1, you get x squared. Set this equal to 0, and solve for x. So I added the 3/2 x squared to the other side, and then if you multiply by 2/3 here to get rid of that fraction, you end up with 48 over 3, or if you cancel the 8 and, I'm sorry, the 24 and the 3, you get 8 times 2. Either way. So normally you would end up with positive and negative 4 here if you take the square root of both sides at this point, but we're going to disregard the negative 4 because it's out of the domain. Remember, it can't be negative for x's. And now this would be where you would make that sign chart. You would say, here's 0, here's the square root of 48, which is 6.9, and then you would throw the 4 in there, and then you would plug numbers into the derivative. Doesn't matter, again, which numbers you pick as long as they're between the intervals. And then this is the first derivative test. So if you pick a 1, this is positive because you end up with 24 minus 1.5. And then if you pick a 5, you'll end up with 24 minus, this is a big number. It'll be like, this is 25. If you throw a 5 in there, you get 25, and then times it by 1.5. It's going to be bigger than 24, so you end up with a negative. So this proves there's a maximum, again, because the tangent lines look like this. And at x equals 4, it's where the derivative equals 0, so it's flat. So that's the first derivative test, proves it's a maximum. Again, I like the second derivative test. So I took this equation, first derivative, and I took the derivative of that. So you end up with just negative 3x. And this time you get to plug in the critical point. So if you plug in the 4, you end up with negative 12. It shows you that it's concave down. So if you end up with a critical point that has this shape, then it proves it's a maximum. So now we have our answer, x equals 4 is going to give us the maximum volume. The question is asking to find the maximum volume. So now we just actually need to go and plug it into the volume equation. Here's the volume equation that we found. And, we could try to figure out what y is. Like we can go back here and stick x equals 4 into this equation and find y, and then go back to this equation, but why bother? It's all equal. So let's just use this equation. Or it doesn't matter. Any one of these volume equations works. This is the easiest one. And plug in your 4 and get 64. Don't forget the units on these. I think I forgot the units on that last problem. But don't forget the units when you're talking about these ones. 64 centimeters squared. I'm sorry, centimeters cubed. That's a mistake there too. Ugh. Sorry about those. All right, hope this helps.